Hello, George Romanic here. Today we are going to talk about pressure. What is a pressure of a gas? For example, in your room where you are watching this video, there is air, you are breathing it. And that air exerts pressure on the walls of your room, on the monitor of your phone or computer, on your body, on any object whatsoever. So what is that pressure? Of course, many people would say, well, pressure is force per area. But that still doesn't give us the phenomenological nature of pressure. What does it represent? One way that all of us experience pressure is thanks to our eardrums. If you fly or you suddenly change altitude for whatever reason, for example, you're skiing or something like that, you sometimes feel hopefully mild pain in your ears. And that's eardrums. Eardrums are very sophisticated membranes, and there is air on both sides of eardrums. Air inside has certain value of pressure compared to the outside environmental atmosphere. If these two pressures are approximately equal, then you don't feel anything in terms of uncomfort or pain. But if it happens that pressure on one side of the eardrum is much higher than the pressure on the other side, you feel that as the pain because eardrum deforms. Now that deformity can be mild, it can rupture, or you can have permanent deformation, so it can be a serious problem. But what is that pressure? Well, that pressure actually is particles of air, atoms and molecules in air hitting your eardrum. When the pressure on both sides of eardrums is the same, then particles hitting from this side are hitting it approximately equally as the particles hitting eardrum on that side. But when there is a pressure difference across eardrums, then maybe particles inside are hitting it like that, but particles outside are hitting it much harder. And as a consequence, in this case, eardrum will deform like so, because we would say there is higher pressure on this side of the eardrum than on that side of the eardrum. So basically, in one sentence, that's the pressure. It's the bombardment of particles of gas onto a surface. Now, that surface can be real surface, or you can put some imaginary surface and analyze the pressure across that imaginary surface. That's the qualitative explanation of the pressure. Now we dive into beautiful derivation of this theory. Let's do it. Let us assume that we have a box, like this one, let's say, and there is a piston. Now, in this box, there are atoms, and we will assume that these are monoatomic atoms in the box, and you will see towards the end of the video why. This box has volume V, and the piston has area A. Let us assume that this box is placed in a vacuum. What will happen if there is vacuum outside of the box? These atoms in the box, due to their random motion, will hit the piston. So let's say this one over here will hit the piston and then bounce off. But as it is hitting the piston, and many other of them, it tends to move the piston out. So in order for us to have this piston not moving, we have to exert a force. And the force that we need to exert needs to balance the bombardment of these atoms that are hitting the piston from the other side. What we mean in this situation is the following. Here I have a pretty good piston in this syringe. If I close this opening and now I apply force on the piston, I move it down, but I have to apply force because I'm building up pressure in this chamber down there. And we know that because if I stop applying force with my pointing finger, look, the piston goes up. Now, the force with which I am pressing this piston is equal pressure inside of this chamber times the area of the piston. Again, I know I'm building up the pressure because the moment I release, the piston goes up. We are also, of course, within the context of kinetic theory of gases, assuming that there is no friction between atoms and the piston, between different atoms, and also this piston is perfect reflector. So all collisions are elastic. So let us quantify how much force we need to exert to keep this piston in place in the following way. We will say that force is to keep the piston in place is equal something times the area of the piston. Of course, if the area is larger, there are more these atoms that will hit the piston, so the force that needs to be supplied to keep the piston at place needs to be larger. But what is this something? So force is something times area. And that something is what we call pressure of this gas in the box. So we say that force that needs to be supplied is pressure times area. Or consequently, you can write, if you want, that pressure is force over area. Now, this is good to start with, but we still need to quantify this something. We need to quantify pressure. Because now we just said instead of something, we will use letter P and we will call it pressure, but what is really that pressure? And that's what we will spend the rest of the video quantifying. Let's say that this is my x-axis, and now I apply force. And I move piston, let's say, to this position over here. That means I moved piston for this distance dx. Infinitesimal distance dx. And you can see that dx is in the negative direction of x-axis, so it's going to be negative. Now we ask ourselves, what is the work done on the gas due to this compression, due to moving the piston? Well, work, dW, we usually use W, capital W for work, we know is F dx in principle, namely work is force times distance. But in this case, it is this force times negative dx, because we are compressing the gas. So we rewrite this as minus F dx. So that is the work that is done on this gas. But force is pressure times area, so I can further write that this is minus pressure times area times dx. A dx is volume of the box that is, so to speak, removed from the gas due to the compression. This volume over here. So that means that dW is equal minus P dV. So this is quantification of the work that is done on the gas when we compress it. But still, the question remains, what is the force that we need to apply to do this compression and to counter the bombardment of these atoms? Well, look at it in this way. From each collision, the piston will receive certain amount of momentum. And there are certain number of collisions per unit time, say 1 second. So now this is important statement. Force that needs to be delivered to this piston to keep it in place needs to be such to counter the momentum per second delivered to this piston due to the bombardment of these atoms. Now let us calculate the momentum that atoms give to the wall, to the piston, due to their bombardment. To do that, we will consider the following two steps. First, we will find momentum delivered to the piston only thanks to one collision, one single collision. And then we will multiply that with the number of collisions per second. To do that, let us kind of zoom in of this part over here. So we have piston, and let's say there is this molecule or atom that is heading towards the piston. As you can see, it will hit it, and because the collisions are perfectly elastic, it will bounce off and go in this direction. So this will be V1 initial, this will be V1 final. From my previous video on elastic collisions, we know how to treat these situations. So you can see if this is x direction, and it is the way I plotted it here, that only the x component, V1 initial x, is the one that matters, because the x component is the one that will bring the particle in the collision with the wall, and after the collision this particle has velocity V1 final in the x direction, like this. So we know that the momentum in the x direction is mvx. That is momentum in the x direction. Negative mvx is momentum in the negative x direction of this particle, which means this is before collision, this is after the collision. Which means from this argument, but also I demonstrated it explicitly in my previous video, that the total momentum delivered to the wall or to the piston, let's call P total, delivered to the piston is 2mvx. This is the momentum that particle gives to the piston, and consequently piston also gives to the particle. You might say this is not clear from these arguments. Well, I demonstrated this explicitly in my previous video on elastic collisions. But if you want, this is momentum in, this is momentum out, or after the collision. So the change of momentum will be momentum after collision minus momentum before collision. And if you do these two, you will see that this is minus 2mvx for the particle, and consequently it's the same but positive for the wall, and that's how we get that the wall received 2mvx of momentum. So we found how much impulse the wall or the piston receives thanks to one collision. But how many particles are hitting this piston in a given interval of time, let's say dt? Well, suppose that there are n atoms in this volume. So let's say capital N is the total number. Therefore, I can define quantity small n that will be n over v, and this is number of atoms in unit volume. Excellent. So how many will hit the wall? Well, let us sketch the piston again. So here we have the piston. It has area A. In some time t, only atoms that are moving to the piston and are this distance from the piston will hit the piston. So only atoms that have x component of velocity towards the piston and are this distance from the piston will move the piston. And this distance is clearly Vx times t. In other words, if you want, if there is atom over here that has velocity Vx, in this amount of time t, it will not reach the piston, it will be over here. It will hit the piston later, but not in the time t. In this volume, let's call this volume because this is three-dimensional space, volume of the hit. In this volume of the hit, the number of atoms is area times this height or the distance, which is Vxt, which also means, therefore, from this equation, then that the number of particles that will hit the piston is this volume V hit times n, or that is equal A Vx times t times n, or the number of hits per unit time will be n hit per time is equal A Vx times n. So now this is beautiful result because we can combine the amount of momentum that one collision delivers to the piston with the total number of collisions in a unit time to find the force finally exerted on this piston by the collisions. So A, first we find force of one collision. So force 1, just of one collision, this guy over here, is equal change of impulse P total over some time of collision, or that is equal 2m Vx divided by t. Therefore, the force of all these n hit collisions will be, well, force of one collision, 2m Vx divided by t times n hits, and that is A Vx times n times t. That's n hits, as you can see here. Time and time cancels, and we get that the force is equal 2 times m times n times a and times Vx squared. Or consequently, pressure, that is force over area as we define above, will be equal to 2n m Vx squared. So we define pressure, we define force. But before we start celebrating, there are several very important details that we need to notice to make sure, or rather to adjust these equations to make sure they are correct. Because in the form that we have them now, they are still not correct. So what are these subtleties? The first subtlety that we need to account for and recognize is that in this volume and in the entire gas in this box, it's not true that the x component of all atoms is this Vx. Some atoms are moving faster, some atoms are moving slower in that volume. So to account for that, we take average of this. So we say that real pressure is really 2n m average of Vx squared. So not square of the average, but average of squared velocities. The second subtlety, and hopefully some of you already noticed, that in this heat volume, not all atoms are going towards the wall in terms of the x direction. Some of them are going towards the piston or wall, some of them, maybe this guy, is going in this direction. And this guy will not hit the wall. So really, the total number of atoms hitting the piston is not this, but rather half of that, because only half goes in this direction of the x-axis, and the other half goes in the opposite direction. Which means that the correct expression for pressure becomes this divided by 2, and that is n m average of Vx squared. And this, my dear viewers, is the quantification of pressure using kinetic theory of gases. So we saw that pressure is, but because there are no external forces and none of the directions in the gas is preferred, that also means that Vx squared averaged is the same as Vy squared averaged, and that is in turn the same as Vz squared everything averaged. None of the directions in the gas in the box is to be preferred, which means that the total speed averaged is equal, well, just this, Vx squared plus Vy squared, but that's also Vx squared averaged, plus Vz squared averaged, but that is Vx squared averaged, which means we get that this is 3 averaged Vx squared. Which further means, of course, that this Vx squared averaged is simply three-dimensional speed, total speed, V squared averaged divided by 3. So if we insert this over here, we can rewrite our equation for pressure to be n times m V squared divided by 3. However, we tend to write this equation slightly different, and you will soon see why. We write it that P is equal 2 over 3 n times m average of V squared divided by 2. So you can see 2 and 2 cancels, and I just end up with this 3. But the beauty of writing it this way is that I hope you can recognize that this term over here is kinetic energy. We can go even one step further and multiply this by the volume, and then we will get that PV is equal n times volume. We saw from the previous page that that is total number of particles in that volume V. So that is n times this 2 over 3 n times this kinetic energy m averaged V squared divided by 2. And this is really amazing result. Together with this result, of course, here we directly quantified pressure in the gas thanks to bombardment of atoms, at the end of the day using only Newton's laws of classical physics: elastic collisions, conservation of energy, conservation of momentum, and so on. Furthermore, this quantity n, m, averaged V squared over 2 is called internal energy of the gas, and we use letter U to denote it. Which also consequently means, of course, that we can write this equation that PV is equal to 2/3 times U. However, historically, this equation is quite often written as PV is equal gamma minus 1 times U. Now, why this complication? Why not writing it like that? Well, at the very beginning of the video, I told you that this whole theory is developed for monoatomic gases. And for monoatomic gases, this works in the current format, and you get this coefficient 2/3. If you repeat this for multiatomic gases, then this is not necessarily 2/3. So, to account for different values of this coefficient for different types of gases, they write this coefficient in this form, where you can see that gamma is 5/3 for monoatomic gases, such as helium or argon or something like that. This formula is remarkable because intuitively it tells you if we have fixed volume and we increase internal energy of the gas, and that means we are actually heating up the gas, keeping the volume constant, pressure will increase. And you see that every day in your oven. You have oven, let's say here, you have oven, there is some baking going on inside, but what is really happening, volume of your oven is fixed. Heat is pouring in thanks to heaters that you have. So internal energy is increasing in your oven, volume is the same. Consequently, thanks to kinetic theory of gases, pressure needs to increase. And this is exactly what happens, because when you go to check on your pizza and you open the oven, the hot air hits you in the face. And that's thanks to this law over here. We will later explore this in more details in separate videos, but for now you should be able to understand it just looking at this equation over here. I know this is a long video, but this is extremely important video because we just quantified the pressure of the gas. To get some intuition for this, let's look at one example. Let us say we have this box, and this is 1 cubic meter, 1 meter, 1 meter, 1 meter. And we have gas in the box, it's monoatomic gas. Volume of the box is 1 cubic meter. Pressure is 1000 millibars. So it's just room pressure. If you took one box of helium in your room, nothing special. 1000 millibars, we want to move this to pascals, that's 10 to 5 pascals. Now, root mean square velocity of helium atoms, and I'll explain soon what root mean square velocity is, but root mean square velocity of helium atoms at room temperature, let's say around 20 degrees, is 1300 meters per second. So V root mean square, VRMS, is 1300 meters per second. Given these, calculate how many atoms of helium is in this box. Well, this is not enough because we also need to know the mass of one atom, but we'll get to that later. How would we calculate this? Well, very simple. We use our equation that PV that we just derived is equal N 2/3 m average of the squared velocity divided by 2. So you see that 2 and 2 cancels. Volume is 1. Pressure is 10 to power 5 pascals. And now we also need mass of 1 atom of helium. So I checked online, and mass is approximately 6.6 times 10 to power negative 27 kilograms. Well, that means that N is equal 3 times 10 to power 5, that's pressure, and this 3 is this 3, divided by M, 6.6 times 10 to power negative 27 kilograms, and times this average of the square velocity of all these atoms. We don't have this, but we have VRMS. And root mean square is the following. VRMS is defined as, well, the word says, that's the root of the mean squared velocity. So root of this. And we usually give information about this as the root mean square velocity because this has units of meter square second squared, and then it's not convenient to call it velocity, but once you take root, these squares disappear, and that's useful. So if we square this, we will get that VRMS squared is equal this. And now what we need to do, we just square this value of velocity, plug it in here, and we will get, if I calculate this correctly, please check because I only do calculation once, 2.7 times 10 to power 25 atoms. This is how many atoms we have in the box at these conditions. Now I did this example for mainly two reasons. First, it's absolutely beautiful to do these examples, and I could do it for years. But the second reason I wanted to do this example is to demonstrate how kinetic theory of gases relates macroscopic quantities like pressure and volume to microscopic quantities like number of atoms in a box. So we have input variables that are something that we sort of say can see with our own eyes, volume of 1 cubic meter, pressure of 1000 millibars, and so on. And we use physics, kinetic theory of gases, to figure out how many atoms is in this box and how they exert the pressure that we measure using an instrument that you can buy anywhere in the store. This video answered the question, what is a pressure inside of a gas? And we also introduced the concept of internal energy. So if you only watched this video, you should already be able to answer the following question. If I take this very simple barometer, this part of the tube is exposed to our atmosphere environmental pressure of the atmosphere. Inside of this container, filled with simple water with color, with food dye, is also pressure that is equal to atmospheric pressure because this liquid needs to adjust so that pressure through this tube is equal pressure inside of the container. Internal energies of particles, atoms of air inside of this container and ambient atmosphere are the same. However, the question is, what will happen if I add internal energy to the air inside of the container? And I do it by providing heat of my body. Let us see. Do you see this liquid climbing? Why is the liquid climbing? Look, I am providing internal energy to the air inside of this container. If I am increasing internal energy, what is happening to the pressure? Pressure is increasing. Pressure is increasing means higher pressure on the walls of this container, on the glass, but also higher pressure on the liquid inside of the glass container, and consequently the pressure is pushing liquid up. So now, thanks to me supplying internal energy to the gas, air inside of this container, I increased pressure above the value of atmospheric pressure inside of this room where I'm sitting. If I add even more internal energy, perhaps this liquid will go even higher up. Yeah, I can see it a little bit going up. Now, what will happen if I just remove my hand? Let's observe this together. The liquid will start going down. I can already see how it's slightly moved down. I hope you can see the same. Yeah, definitely. There is no more liquid in this wider part of the tube. Now the liquid is descending even further down. I hope you can see this on the camera. This is absolutely amazing, beautiful experiment that you can do at home if you buy this for $5–10 online. Look how liquid is going down. Why? Now you should be able to answer that. Well, because the internal energy that I supplied to air inside is being dissipated to the atmosphere, because atmosphere is much larger than the air inside of the container. The energy, internal energy, is lost. And therefore, pressure is decreasing. And as the pressure is decreasing inside, well, the liquid is being pushed down more and more. And there is no need for me to hold this more. I think I demonstrated the concept that the liquid goes up, and now after I stopped supplying internal energy, the liquid goes down. Notice how throughout this explanation, I never used the word temperature, because we still didn't define the concept of temperature. I will reveal that now, that of course increasing internal energy of the gas means increasing temperature. But I didn't want to use that phrase because I still didn't properly define temperature the way I define pressure today. And that will be in one of the next videos. Until then, goodbye.